Study with Steph, cause she's the best. She's gonna help you get your CTS, yeah.
Ain't nothing can keep me down.
Stephanie.
Hey everybody, welcome to episode 4 of Study with Steph. In case you don't know where you are, what you're doing, I am on a mission to get my CTS, so I began this podcast to help myself as I start studying and to hopefully help all of you out there who are doing something similar to what I am doing. Today we are talking about audio, and I have invited the audio man himself, Chuck Espinoza, on with me to talk a little bit about this chapter because help. So, Chuck, thank you so much for joining me today. I really appreciate it.
My pleasure. My pleasure. Glad I could be here.
So I talked to you a little bit about this, but I am coming from a little bit of experience with audio just because I studied radio in undergrad and graduate school, and I would go out into the field and I would use microphones and loudspeakers and these things. So I kind of understand what they do and why they're important. But when we talk about the science and the physics and the inner workings of why they work, that was when I was like, oh, maybe I really don't know audio as well as I thought I did. So I really appreciate you being here. So I guess it might be easiest to start with the simplest way to talk about sound, which is in sound waves.
Right. So sound wave, sound is made from energy. Something has to produce some type of energy. And the way that energy transfers, like from my mouth hole to your ear hole, is I vibrate air, the molecules in the air. When my vocal cords move or when any sound is made, there's air molecules all around us. And the sound is made and it upsets those air molecules. And one molecule goes forward and it bumps another molecule, so to speak, and it kind of makes this chain reaction. And it's, when the molecules come together, it's called compression, when one molecule gets closer to the other, and then rarefaction when it separates, and it's like domino effect, right? So
right.
That being said, sound in all audio and all types of sound, it's an energy. It's got to be created with some type of energy. We have to have some type of impulse of energy to move that air. And once you really wrap your head around sound being a physical thing, not just something that, it literally floats in the air, but it moves the air around, you can start seeing how some of the things to control this sound are a little bit different, like sound absorbers, or why do we have reflections off hard surfaces, off specular surfaces? Why does it sound funny when I'm talking in front of a mirror? I have more high end than when I'm talking in front of drywall. So once you grasp the whole concept of this sound is energy, then we could start talking about different things like frequencies and wavelength. But the basis of everything is sound is a form of energy that moves molecules around the air, and our eardrums, our microphones, our ear holes are just like microphones. They pick up that sound and, it vibrates, that air vibrates our eardrums at different frequencies and amplitudes, and it changes it into an electrical impulse that our brain can understand, or the microphone will change it into an electrical impulse, the actual voltage that we get and can reproduce and amplify and play with and send across the country.
So when we're looking at a sound wave, like a sine wave, we measure it in terms of wavelength and frequency and amplitude.
Yes.
So wavelength is, if I'm understanding, from point A over here to point B, how long it is, this one wave.
Yeah, that's kind of a way of thinking about it. The sine wave is going to cycle.
Okay.
So when I put some energy in the air, it's going to hit this molecule. This molecule is going to hit this molecule, et cetera, et cetera. Now, if you think about that in terms of what it would look like linearly from the side, the sine wave would get some power and go up to its 90-degree position, its first hump in that 90-degree position, and then it would go back. So the molecule would go forward and then back to where it was originally at. So up, and then back down to its 0 position, but that would be 180 because now it's not going up, it's going down.
Mm-hmm.
So up to 90, back to 180, and then the molecule would actually come back. So you have the compression, I'm pushing it away,
Mhm.
and the rarefaction back from the other molecule. So it would go up, come back towards me, and then back to its 0 position where it would start going back up again. So that's how the sine wave would vibrate, and that's how it would look linearly, or if you're looking at it in front, it would go from here. It starts here.
Okay.
It forward, back, back, forward, back, back, forward, or up, down, down, up.
Okay.
So that's how the sine wave would function. Now that sine wave, that molecule, has a physical a distance that it's going to move per frequency. If I was to time sound in a given space, how long it takes sound to move, it's about 1,130 feet per second.
Okay.
So that would tell me that a 1,130 hertz, 1,130 vibrations per second, that would, each of those vibrations is going to be about a foot long.
Okay.
1,130 feet per second. So a 1,130 hertz sine wave, the distance it's going to go is about a foot, roughly speaking. So that's how we would talk about frequency, is how many times per second does this sine wave happen? It's
Okay.
literally frequency. How frequent does this sine wave happen? So when we talk about bass tones, or like very low frequencies, like 60 hertz rumble in my car stereo, those frequencies, you can actually watch the loudspeaker vibrate 60 times a second to make that 60 hertz wave. And it's a very big wave. The 60 hertz wave, for it to actually cycle, is huge.
Yeah.
If you think about a wave that's 1,130 hertz is a foot, well, if I halved the frequency, if I cut that frequency in half, I went down an octave. An octave is a doubling or halving of the frequency. So if I move down an octave to 565,
Mm-hmm.
that sound wave at 565 is 1 octave below, but it's twice the size of that 1 foot sound wave. It's physically twice the size. So the molecule is going to go forward and back a lot longer distance. And if we 565, we go down another octave to 282.5. Now that is 4 feet long, and we can keep going, dividing those octaves and going down and figuring out what that physical wavelength is. If I got my calculator here, let me grab my calculator.
Okay.
I'm going to go 1,130 feet per second. 1,130 hertz is a 1 foot wave. Divide that by 2. 565 is a 2 foot wave. Divide that by 2. 282.5 would be a 4 foot wave. Divide that by 2. 141.25 hertz would be an 8 foot wave.
Okay.
Divided by 2. And a 70.625, 70 hertz, 70.6 hertz would be about a 16 foot wave. It would take that wave 16 feet to actually cycle in the air.
Okay. Got you.
Cool.
So next, you talked about octaves a little bit, and I want to kind of jump into those a little more, because I do understand that, like, we hear sounds kind of based on octaves. And octaves, I know that it's like, there are 8 notes in each octave. And, like if you're looking at a piano, it's like A to A or B to B. Like, I know that. But when it comes to like putting in the harmonics and understanding how we hear sound on a logarithmic scale instead of a linear scale, that's where I'm getting a little confused.
Okay, so we have 2 different things going on. Number one is going to be that, say that low C, the white key, right?
Yeah.
So an of that, the same kind of looking key. It has the black key next to it, and you know, below it the B is the white key. If we hit those two, bing, we are playing an octave.
Yes.
Well, when I hit that low octave, that fundamental note is going to generate within its own sine wave. It's going to generate other sounds. There are going to be more frequencies created by that fundamental. So we have our fundamental octave at the bottom. The first frequency it creates is going to be a octave above it, just from generating that note. When it starts moving around, we are going to hear an octave above it. So that's the first harmonic it's going to generate. So then the next harmonic it's going to generate is a fifth above that. So if it was a C, it would be generating a G, an octave and a fifth above it. Then it's going to generate another octave, so the third octave. And then it's going to generate a third, a fifth, so C, E, and G, like a chord. And then another octave above that. And then after that, it's going to start generating some weird harmonics. In the music spectrum, it would be the fundamental or the root fifth harmonic, and then that would be considered one. We're going to generate the second note, which is a step away, a flattish third note. So it's a little flat. It's not quite a perfect third.
Mm-hmm.
A little bit of a sharp fourth, the fifth, the sixth, a seventh, but just a not quite a perfect seventh, and then the final octave up top. So we have this 5 octave range: fundamental, first octave, fifth, second octave, third, fifth, fourth octave, 2, 3, 4, 5, 6, 7, fifth octave. And that is a full overtone. So when I generate a note, if I hit that low C, bing, it's not going to come out just one perfect sine wave. It's going to come out with all these overtones that play into it. Now, it's really, unless you're really trained or you listen for them, you really don't hear all of these things generated. But it would be, you know, every now and then, if you could sit down on a piano and guitar and start playing these octaves, and you can kind of start hearing these tones generate. But the energy that fundamental is generating to generate those tones are not what's struck. It's usually just the fundamental.
Right.
That's a lot of very low energy. So you really have to listen hard, be in a very quiet environment. So that's the first thing we talk about. So that is frequency. When we talk about decibel, that has to do more of with amplitude, how loud this is, how much power this thing has.
Okay.
And a decibel by itself doesn't mean anything. When I say 25 dB, that doesn't mean anything. A decibel is a comparison between two numbers. So I would have to qualify that decibel. So I would say 25 dB SPL. So now, if I say 25 or 35 dB SPL, I'm qualifying that as a comparison to 0 dB SPL. Like, you can't hear anything, 0.00002 pascals of pressure where there's no sound. And then logarithmically, I would work my way up. So let's talk about linear and logarithmic. Linear, if 1, and this is 1, I have 2, right?
Yes.
So 1, the next step is 2. If I add another one, it would be 3. It would be 3 individual ones. Linearly, if I have 1 and I went up and added a 0, now I would have 10 logarithmically. Then if I add another 0, I would have 100. So if I'm talking about steps in a bell system, which is what our logarithms are based off of, first is 1, then 10, and then 100, and then 1,000. So you can see if I get up, if I say something like it's an 85 dB difference, that's massive compared to like a 15 dB difference. It's not just 70 of the same thing. It's going up like this into a huge difference. So the difference between 3 dB and 30 dB is, it's not like I'm just adding 27 of the same thing of 3. I'm actually going logarithmically, exponentially out. So linearly, when we listen to music, like on our volumes, on our radios and iPads and things like that, and we actually turn a volume knob up, it goes from 1 to 2. 1 to 2 is linear for our thinking, but it's actually going up logarithmically. It's increasing in multiples, because if I moved it up 1 dB, if I went from 1 to 2 dB, I wouldn't notice a change at all. If I went up from 1 to 3 dB, I might barely notice a change. If you can imagine a volume knob that went from like 0 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000, 10,000 to 100,000, you know, we'd have, it would just be like, hey, can you turn that up to 100,000?
Okay.
So when we talk about decibels, we're talking about comparing one thing to another. And in the case of loudness, we're talking about pressure. 94 dB SPL is 1 Pascal.
Okay.
0 dB SPL is 0.0002 pascals. So now I have from literally 0.00002 to 94, or 0.00002 to 1 to go from 0 to 94. I have all these little cuts in between, all these little, you know, that's a lot of numbers in there to be able to stop. So instead of labeling things in the Pascal, the pressure, the standard unit of the Pascal, we start as a comparison just using the dB for SPL. And we do this with electronics. We compare voltages with dB. We compare outputs of power. Like if I have a 10 watt amplifier and I want an amplifier that's twice as loud, I would do 10 log 10. I would do a 10 log calculation. So my calculation, my amplifier, let me do this real quick.
Okay.
If I'm doing I have an amplifier that's putting out, say 70 dB SPL.
Okay.
I'm going to get an amplifier twice as big. So I'm going 10 log 20, which is my variable, twice as large, divided by 10, which is my reference, my 10 watt amplifier. What happens if I get a 20 watt amplifier? That's a 3 dB increase. So if I'm listening to music at 70 dB at a 10 watt amplifier and I up my amplifier to 20 watts, that's going to be 73 dB. Well, that's not loud enough. I need another 3 dB to actually notice the difference and make the change and make me happy. So now I would have to take that 20 watt amplifier and double it. I couldn't just say 10 to 20 gives me 3 dB. If I add another 10, that's 3 dB. Nope, it's not. 10 to 20, that change, that doubling would be 3 dB. Then I would start at 20. 20 to 40 would be another doubling. That would be 3 dB because it's a comparison. So 10 to 20 is a doubling. 40 is a doubling. Every time I double power, it's a 3 dB change. This affects us when we have things like, so I have a concert system that's supposed to be, say, 100 dB at mix position, and I have 10 loudspeakers on each side. My mix position, I'm getting a 94 dB SPL with it at RMS, at average, what it's supposed to be. 10 loudspeakers, 94 dB. Okay, I double that to make 20 loudspeakers each side. I just got to 97 dB. Now I put 40 loudspeakers each side, then I get to 100 dB. So you can see when I start getting bigger and bigger, like I really get big. So that's kind of how the decibel works when we're talking about physics of sound.
Got you. That makes more sense to me. Thank you.
Good.
So
Good.
Next, when it comes to like the inverse square law, can we talk about that really quick? Okay.
Okay. I'm going to give you the general principle, and then I'm going to talk about something that's going to blow your mind, and everything's going to snap all at once.
Okay.
When I double the distance from a sound source, right? My sound is, say, at 2 feet, and I go out to 4 feet, I lose 6 dB. Or if I'm at 4 feet and I go to 2 feet, I gain 6 dB.
Okay.
Now, this is weird because if I double or half power, it's only 3 dB, right?
Mm-hmm.
So inverse square with sound, if you can imagine sound as light, And it works the same with light. If I double or half power with light, it's a 3 dB change. Now think about it. I have this box, right?
Yeah.
This is the area my sound is energy is being put out. If I doubled this, I would put another box next to it, correct? So now that's 2.
Yep.
So 3 dB. But if I move from here and I double the coverage from that to that, that's not doubling the coverage. I have one here, 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 and here. So now I have 4 boxes. So these 2 boxes, this box by itself is the sound. I add another box, it's 3 dB. But now I'm doubling this for another box to give me my square. So if you can imagine with light, the amount of light that's covering this area, if I move my flashlight back, so now it got bigger, now I have 4 boxes. The same amount of light is covering 4 boxes. So the intensity, the power of the light goes down 6 dB.
Gotcha. Okay.
So that works with sound, with light, that inverse square law. If I double the distance or half the distance. Now this is specifically with distance and power, the power intensity of a light or the power intensity of a loudspeaker. So this works if I just have a normal loudspeaker. Hey, check this out. I'm totally going to blow your mind. There's loudspeakers that don't lose 6 dB when you double. If I double the distance from a line array, because the pattern now is not like a sound goes omnidirectional. If I had a theoretical loudspeaker in my thumb, right, it could generate every frequency, but there's no box, there's no transducer around it blocking the sound waves. The sound would go everywhere in a 360 degree, like a sphere, like light with a candle. If I have a candle, that light goes everywhere.
Right.
So the only thing that really keeps my music on a regular box loudspeaker going forward is the medium of the things. Those sound waves, those higher frequencies that are like, half an inch, those are being blocked by the back box, by the cone, by the spider of the loudspeaker. That's why people say bass is omnidirectional. No, all sound's omnidirectional. The bass frequencies that are 10 feet long aren't being blocked by that 2-foot piece of wood in that loudspeaker. To block a sound, I need something that's at least the size of that wave. So if I have a loudspeaker that through design and construction is made to not throw out like an orb, but throws out its pattern like a soup can, now I've focused all that energy like a line array. Well, instead of losing the energy that would be going this way, we focus that energy on a line array loudspeaker. And just like light, instead of having a candle, it's a laser. And that light or that sound maintains that focus of energy over a distance. So now I only lose 3 dB every time I double the distance with a line array. Or fluorescent lights. Fluorescent lights, the pattern that a fluorescent, like a 2-foot tile light or a 4-foot tile light, fluorescent lights, those throw their light pattern just like a line array. And I've done this in class many times. We go to like an incandescent bulb and I'll hold up my light meter and then I'll double it and we'll do the calculation. And sure enough, we lost, when you double that distance, think of those squares. Now I'm doing light over double the distance. So I have 4 squares. So each square now only has 25% of the original energy. So if I'm at 1,000 lumens or 1,000 lux, excuse me, not lumens, 1,000 lux, and I double the distance, my measurement's going to be around 250 lux at that double distance.
Gotcha.
So I can go up to a fluorescent light. I'm at 1,000 lux. I double the distance. I only drop to 500 lux. And I do this all the time in class. It's really freaky. People are like, wow, the fluorescent light doesn't lose as much energy. And we talk about the focus of that energy. And energy, a sine wave is a sine wave. These fluorescent lights coming off as a sine wave, it's just a higher sine wave, higher frequency, right? Light's just a sine wave in a higher frequency. Sine waves behave the same. If I can focus them and get all that energy captured, I can use less energy to get the same amount of coverage. Line arrays, they're meant, big concert speakers, they're meant to throw way back to the back of the crowd. So I want to get back there and I want to have my 100 dB SPL at mix position instead of adding 40 speakers or instead of going up to 40 speakers per side to make that 6 dB, now I'd only have to use 20 speakers per side.
Got you.
So that's how we start using physics to our advantage.
Okay.
You know, the right kind of equipment to spec when we know, hey, I know we're going to be thrown a long way with our light, so why don't we use fluorescence here instead of incandescence, et cetera, et cetera.
Moving right into acoustics now. So it's a whole branch of science, which like the word science by itself, I'm like, oh no. So it's basically the science that's behind the characteristics of sound waves.
Right.
Okay, great. I've got it so far. So reflected sound energy, like when you are talking into a room, no matter what room you're in, like sound at some portion, unless you're in like a very special room, is going to reflect.
Yes.
And there are two types.
So there's the two main types of reflections are specular and diffused.
Okay.
So let's think about this again like a light.
Okay.
If I have a matte screen and I shine a flashlight on it, that flashlight is going to hit the matte screen and it's going to diffuse that energy. We're still going to have a basis of our energy, but it's going to diffuse that energy. I'm not going to see a laser-like reflection. It's going to, you know, light up the room, so to speak, especially if I have a very even light on it and an even flashlight. Now, if I had that same flashlight and I had a mirror, that light is going to hit that surface, that specular surface, and angle off at the same angle that it hit, the angle of incident. So if I'm standing next to the matte screen and I see it, I can go around and I can see that light all over the place because it's diffusing. But if I'm on that mirror and somebody shines a flashlight, there's only going to be one little spot that I would be able to see that light because it's hitting and directing right off in its same focus beam. It's not being diffused all over the place. Same thing with sound. So the two big reflections are specular reflections, that laser-like thing, and diffused reflections. If it hits it and diffuses that light or sound in every direction.
Got you. Okay. Moving right along into sound capture. So I obviously know what a microphone is. So I'm kind of coming along. But the way that they work is different. So that's where we bring in dynamic and condenser and electret and was it MEMS or MEMS? I've never even heard of that. But like most in my line of work, I knew it was a dynamic because those were cheap. We could carry them around with us and nothing would really happen to them, and they were the easiest to just like bring around with you in a handheld. So yeah, so is it the difference between like all of these, how they are built on the inside? Okay.
How they're built on the inside and actually what they do. So
Okay.
a dynamic mic, it's very, very simple principle. You have a piece of wire and you wrap it around a magnet. Just coil copper cable around a magnet and it comes out the other end. Now, if you've ever done this, I have this thing I play with. I have LED lights that I have a little LED and I have a piece of conduit. It's just plastic conduit. And the LED has a piece of copper wire on it and it's wrapped around the outside of the plastic conduit and then connected to the other side of the LED. And I have a magnet that I push down that's the same size as the conduit. And when that magnet passes the coil of wire, the LED light lights up. It creates a charge. Magnet moving with copper wire creates a charge. So now we can create a charge. Remember I said my mouth hole is going to vibrate the microphone and it's going to create an electrical impulse. So microphones they actually create electricity by doing that. But to do that, I have a diaphragm, very, very thin piece of metal. And when I say thin, like most diaphragms are either plastic or metal. The really good ones are metal, but they're like 2 or 3 microns, maybe even 6 microns thick. And when I say 6 microns thick, your fingernail grows 10 microns an hour.
Okay, so very small.
This thing is 6 microns thick.
Okay.
Very thin, right? So the sound hits this diaphragm and it vibrates. And the diaphragm is connected to the magnet and the coil wire. And so it vibrates, this magnet, creating a very specific electrical charge that is consistent. So I put the energy into the air vibrates the molecules vibrate the diaphragm vibrates the magnet, the magnet gives a charge of that vibration to the microphone, and that's what creates our signal in a nutshell.
Okay.
So it transduces that energy. That's a dynamic microphone.
The condenser has like capacitors, right?
Yeah, there's a bunch of electronics in there. The big things about condensers is there's 2 plates, right? Instead of a coil of wire,
yeah.
And we run a charge through this. And when the diaphragm vibrates, it changes the amount of charge between these 2 plates. And that's what we're recognizing as the signal. We have to run some type of power to get that charge, phantom power, right? The nice thing about this is I can use smaller microphones. I don't need a big diaphragm, to generate that charge. I'm just looking at the difference in this charge. So I can use a lot smaller diaphragms. They're more sensitive. So that's just 2 of the mics. There's all kinds of different microphone construction. There's laser mics that pick up the change in the molecules through a laser. There's ribbon microphones that, it's literally a ribbon of metal stretched across. There's a bunch of different pickup patterns. Microphones are designed through that physics to pick up like a cardioid pattern, right? If I have my microphone here, I just want it to pick up in front of my face. I don't want it to pick up what's back here. Or I might have a microphone that's a hypercard where it's very, very tight pickup area. So if I move the microphone off axis, it wouldn't pick up as well. But the advantage to this is on a cardioid mic, that off axis rejects really well. So if I'm a lead singer in a band and I have a monitor in front of me, I can put that monitor in front and it rejects that audio. If I have a lead singer come up and say, hey, I want 2 monitors, I change the microphone out. I give them a supercard or a hypercard. That way it rejects off the side. It still has a little bit of pickup. If you could think of this pickup area as a balloon. So if I have all balloon here, I have none here. If I squeeze this balloon, a little bit's going to come back here, but I'm going to have rejection on the sides because I squeezed it this way. If I squeeze it even more, very tight, I might have a lot more pickup from the off axis, but it rejects that much more on the sides.
Moving along to audio signal levels. That was like the next thing that kind of stumped me a little bit. So in terms of mic level, like I understand what that is, because like if you plug your microphone into a recorder and you like listen to it, it's gonna make a noise even if you're in like the quietest room ever, and that's just what mic level is, because mics just automatically come with like a level of noise, right?
So yes and no.
Okay.
So when we start,
that's fine.
We have to look at the specifications of a microphone and how sensitive that microphone is. So a lot of microphones have a sensitivity on their spec sheet compared to 1 Pascal. That's pretty general. They say if I put 1 Pascal of energy, remember that those microphones are generating an electrical signal. So if I give this so much acoustic energy of 1 Pascal, it's going to generate an electrical signal of this much dBV. And remember, dBV is a comparison. I qualified that dB with a little v. So I'm comparing what this microphone is giving me. If I put this much acoustic energy into it, how much power is that microphone going to give me as compared to 1 volt? 0 dBV is 1 volt. So if I'm putting, say, SM57, it's not jock and manufacturer, I just know off the top of my head, my SM57 is negative 55.4 dBV at 1 Pascal. So now that I know this ratio, if I have less than 1 Pascal, less than 94 dB, a human talker is 66 dB at 66 to 70 dB at 1 meter. So if I have this microphone 1 meter away from my mouth, now I'm not giving it 94 dB SPL. So it's not going to give me 54.5 dBV voltage. It's going to give me a lot less. And I can do some math and a comparison. I actually have a bunch of videos on our video series for AVIXA, telling all about this. So we go through microphone comparisons. So if I put in more, now think about this. Lead singer, and I do this all the time with my lead singers. I just put an SPL meter by them and say, can you sing into this microphone for me, and hold it like you would. And they sing into it, and their voices are powerful. So at this distance, 66 dB in normal talker at 1 meter, but someone singing at this distance is going to be a lot more pressure because the microphone's closer, because their volume's raised. So a lot of lead singers will generate between 105 and 110 dB SPL at the microphone. So I've compared it to 94 dB. I'm going to get negative 54.5 dBV, and I can think about that in my mathematical comparison, figure out how much gain I need, et cetera, et cetera. Well, now I can move that 94 dB SPL, because we're dealing in dBs. Again, it's a comparison, to 110 dB SPL, figure out how much dBV it's going to output, transfer that to dBu, what I'm going to have in my console. And dBu and dBV, there's a 2.2 difference because dBV is a 1 volt reference. dBu is 0.775 volts. There's a 2.2 dB difference there. Then I can figure out, well, my lead singer is 110 dB SPL. With this microphone that's negative 54.5 dBV at 94, that means I'm only going to need about 28 to 30 dB of gain. So before I even get to the console, before I even plug anything in, I know what my microphone is. I know what I have a guess about what my lead singer is going to do. I can set up all the gain knobs. If it's a DSP, I can do all my programming before I even get there. So all of that stuff, all of these things work together as a system. Right. Knowing the microphone specs, getting that microphone level. Now, when they talk about microphone level, if I had a dynamic mic and I talked into it and put a multimeter on it, or gave it some consistent sound energy and put a multimeter on it, that microphone's only going to generate like 0.002 volts or 0.003 volts. So microphone level is very, very low electrically. When I put it into a mixing console at my preamp, that's where I want to bring it up. Now, preamps will do that cleanly. They will isolate it. They'll give me a nice signal before my noise floor. My noise floor, what I'm going to hear from that console. And like you said, you turn it on, nothing's going through it, and you can hear, right?
Yeah.
So I want that noise floor really low. And I want that signal to be 60 or 70 dB above that noise floor to make it nice and clean. So if I have a signal coming in that's 0.002 volts, and I don't bump that signal up on my gain stage, if I tried to amplify that signal, my noise floor is at like 0.001 volt, and this microphone is at 0.003 volts, right? If I don't amplify that mic signal before it gets to the noise floor, before it hits the electronics, when I go to amplify it, I'm amplifying my signal and my noise. That's what's coming out of the loudspeakers. So at the gain stage, I'm going to amplify that signal over the noise floor. Okay. Now, when it goes through to be processed, you have this 60 dB headroom, and I can hear signal great, and I don't hear the noise. So microphones put out a small charge, but we need, in our preamp section, we really need to boost that up over the noise floor of everything else that's going on.
Got you. Okay, so moving on to audio mixers. So if you have a lot of mics plugged in and you're taking audio from a bunch of different sources, you put it into the mixer so that you can do what you need to do before moving it on to the next stage, correct? And that makes more sense than just like plugging everything directly into like a computer.
Right.
Okay.
So with that mixer, I have all these different points of energy coming in. Let's just think about it from an electrical standpoint.
Okay.
If I have a microphone in and I boost that microphone in that mixer and I get a good level, 0 dBu is what I like to shoot for, nominal, 0.775 volts. Well, if I add another microphone and these microphones are both going to be active at the same time, I just doubled the power. So now, instead of this microphone being 0 dBu and this microphone being 0 dBu, when they're together, it's going to be more acoustical energy coming in, building up. I'm going to have a +3 dBu signal. If I add 2 more microphones, that's another 3 dB. If I add 4 more microphones, that's another 3 dB. Now my signal is getting really hot, right? So at my preamp stage, I want to make sure if I have 1 microphone that's going to be used, I adjust that preamp, bring my level meter up to 0, and it's not going to be a sine wave. Your voice is complex waveform, but it should bounce around 0. If I have 2 microphones, I would set the first microphone, all my faders at 0, and I would bring my preamp so when the person talks on microphone 1, that center of the bounce isn't at 0, but it's at -3. So I know if there's 2 singers singing at the same time, when they both sing, that -3 is going to bring me up to 0. I want to come out of my console at 0 dBu. I'm a unity gain guy. 0 dBu, 775 volts. And I want to carry that through my entire chain. And I do this for math reasons, so I can predict, mathematically what's going to happen to my system. So the more things I add, the more voltage is going to be on my console, the more power is going in. Well, things like if you have a digital recorder, a digital media player, that's not going to be a microphone level. They're putting out, 2 or 3 volts coming out of its output. And when I plug that in, this is one of the cool things. If you ever see a console that says, here's your electronic inputs, they usually have different types of inputs, or even if they're XLRs, you can set it for line level input. There's a button that might say +4 or -10. Consumer gear, stuff with like RCA, their output is usually around -10 dBV, 0.77 dBu. So it's lower. So if I have that button that says -10, I push it and it actually brings the signal up, so I don't have to boost it too much in my preamp. Same thing with professional gear coming in at like 1.2 volts or even 2 volts. There's a +4 button. If I know that professional gear is coming in hot, I hit that +4 button. It's not adding 4 dB to my signal. It's telling the console, this is a +4 device. It's coming in hot. So it actually lowers the sound, lowers the level, And so the something that would be coming in hot, so I don't have to turn it down a bunch, it will pad it for me. And then I have that normal operational sweep, because my sweep's going to go like down at the bottom. It's going to be like -60. It's going to go up to 0 about here. And then +10, +20, +30. Now, remember what we said about dBs. Down here, those adjustments are very minute. Up here, those adjustments are huge.
Crazy, exponential, yeah.
So if I'm working with something that's a huge signal and I want to use the sweet spot of that gain knob, I mean, I would barely be touching it, down here at -60, -50, -40. That's the same ratio as up here is like -10, -20. There's a much bigger area here than here. So if I just moved it a little bit, I might get 6 or 7 dB. Here, I'd have to move it more substantially to get 6 or 7 dB. And that's because the manufacturers know it's exponential up there and we need more room to work.
Okay. Got you. I don't want to take up too much more of your time, but my last question I really wanted to ask you was, it's kind of general. So if you had just like one piece of advice for me as I'm like continuing to study and to really try hard to understand all this stuff, what would it be?
Awesome question. It's a question I'm often asked, and I have the same answer. What you're doing right now, reaching out to your community, talking to a bunch of people who do this all the time, this is the best way to study, to gain knowledge. I still do this. I was on chatting with Bill Natras, Jeremy Elsesser, Jim Maltese today, Jeremy Caldera, people who are very prominent in the industries, are very good friends of mine, but we chat about AV stuff all the time. This is our life. And we get better that way. We build each other up, talking about concepts of business, talking about physics of sound and light, and new product, reaching out to your community. And this whole idea, like, I'm studying, I'm going to make a podcast and get a bunch of people who know more than me to talk about it so I can help everybody else. Yeah. Like, this is phenomenal, to be able to not just get that information, but to give that information. I have a saying that I say quite a bunch. It's each one teach one. And that's the way we get better in the industry. And it doesn't matter if you're an expert, you can always get better. I learn stuff every day. reaching out to people and talking about stuff and not being afraid to ask. I tell people all the time, and if you got a question, hit me up on Twitter, Facebook.
Yeah.
It doesn't matter. Find me or find somebody else and ask the questions. And you came with a good bit of questions, organized, ready to go. Like if I had a day off, I'd literally talk to you for hours about any.
I would talk, like I was like, oh gosh, we've already been talking over an hour, and I could literally ask Chuck all of my audio questions like for hours. So I really appreciate it. And I guess like not having the fear of being like, this is probably going to be a stupid question and I'm going to ask it anyway, because there's no way that I'm the only one who has this question. So
they have been asked and asked and asked. And when it comes to AV stuff, if you don't know, it's not a stupid question. I don't know. The difference between magic and science is understanding where the magic comes from. So like when I tell people audio is not a black art, it's not black magic, it's because I learned the science. At one point in time, I thought it was black magic. I'm like, man, that guy's so good. How can I be that good? And I asked him, hey, how come you're so good? And somebody would show me something. And it's like a wizard showing you a spell, right? And all of a sudden I created a dragon. Well, that's the science to the wizard. To anyone else who looks at it, it's, wow, mind-blowing magic. But no, you do this math, you do these calculations, you take air temperature, learn all the things that affect vibrations in the air. Temperature is a big one. People don't think about that a lot.
Right.
Learn propagates, how it moves around, learn everything about it. And then when you think, I've learned everything about this, find somebody else who knows a little bit more or different. And then you learn from that. And you keep learning all these magic spells to the point where you're like, you get out to the battlefield where your wizards be, and you just throw down some good sound and you're like, boom, done. Like, wow, I'm a scientist. I can show you.
For sure. Well, Chuck, thank you so much. I really appreciate it. I'm probably going to email maybe more questions as I come across them. But I really appreciate it and appreciate you supporting this process that I'm going through. So for everyone listening, you can watch on ravepubs.com. You can also listen there. And I am also on YouTube, Apple Podcasts, and Spotify. So you can listen at all the places. And this has been Study with Steph. Thanks again, Chuck.
Yeah, no problem. I will send you some links too. I have a bunch of videos out. AVIXA has a learning channel on YouTube, and we have a new TikTok channel. So
AVIXA has a TikTok now?
Oh yeah, I'm doing a bunch of videos like learn this in 30 seconds, right? And those videos are assembled off of our learning and training videos. We just take snippets and put them together and give you kind of a taste.
Yeah.
But a lot of those training videos are on our training channel. Some of the videos are behind our paywall. So if you're a member, you can go there and you have access to all of them. If you're not an elite member, you pay a little bit. You can watch a video, get an RU. But I'll send you links to those. If you have any questions that pertain to a video, first thing I'll do is say, hey, watch this video. Go back and watch it a few times, develop specific questions, and then we can talk about it.
Awesome. All right. Well, thank you so much, Chuck.
My pleasure.
Study with Steph, 'cause she's the best. She's gonna help you get your CTS